So it's time to start episode 25 of Warsaw.AI meetups. Hello everyone, thanks for joining today again, and Happy New Year. This is the first Warsaw.AI meetup in 2025. My name is Paweł, as you know, and I will be the host today, but I will be also a speaker. I'm the CEO of the Quantum AI Foundation, which is formally the organizer of Warsaw.AI meetup. We would like to thank our partners and sponsors for supporting us. Allegro Tech, thank you, Teresa, for hosting us for the next time again. So I started collaboration more than 2 years ago, I think. Yes. And we are happy to announce that we continue our collaboration with DataArt. So DataArt also supports the Warsaw.AI meetup and releasing the Warsaw.AI newsletter. And NoMagic. We are also continuing collaboration with NoMagic. As some of you might remember, NoMagic was also the formal organizer of Warsaw.AI meetups when we started this series in 2018. So now formally NoMagic is joining us as another partner. Wow, we started this meetup in 2018. That's incredible. Okay, so as always, we invite you to subscribe to our newsletter if you are interested and would like to stay up to date with all the AI news from the world. It's not easy to follow everything, so we try to give you the curated news from the AI world, of course. And that's the plan. Oh, sorry, that's not the agenda yet. Before I present the agenda, I also wanted to announce some other AI-related initiatives that we have at the Quantum AI Foundation for this year. So in March, there will be an online mini conference on quantum machine learning. It's already the 5th edition. We're also planning to start the first edition of the A-Intern matchmaking program for online internships in AI. We'll see if these internships will be only focused on research or more industry focused, but the plan is to have them during the summer. And there is also a plan to organize the first Warsaw.AI hackathon. Piotr is one of the authors of this idea, so Piotr will also help us in moderating the event today. So the idea is to have the on-site AI hackathon focusing on developing new AI-based products. So during the after party, during networking part, we can also talk more about it. If you are interested in co-organizing this hackathon with us, we can discuss it, of course. And finally, this is the plan for today. So we have the welcome speech, of course. We have a slight delay, but we'll manage. Soon, Marcin Możejko will give a talk titled Beyond Translation, Nature-Driven Deep Learning Architectures for Biological Analysis. So when I told you that we started organizing the Warsaw.AI meetup in 2018, actually Marcin was one of the speakers during the first edition of Warsaw.AI. And the next speaker will be Kateryna Nikitenko from DataArt, our partner. And she will give a talk about empowering personalization, the role of UX in training AI models. And finally, at the end, I will tell you about reinforcement learning in traffic signal control, some recent results that we obtained in the TensorCell research project. And at the end, there will be the after party, so we invite you to stay with us and network with us, of course. Enjoy, have fun, and after each talk, so each talk will last about 20 minutes, and when you have questions, there will be a Q&A, short Q&A session after each talk. Marcin, if you are ready, the floor is yours and we can start.
So, hi everyone. It seems that a lot of people have already submitted their papers for ICML today. And so that's nice. And so basically, let me start with a short introduction and a story that will kind of explain or not explain my motivation to give this talk when Paweł invited me. So my name is Marcin Możejko, and now I am doing my PhD at University of Warsaw. Before that, I think for like 10 years, I worked in industry in different companies here in Warsaw and abroad. I worked for Microsoft, PwC, TCL Research Europe, and other companies. And 4 years ago, I started my journey with PhD studies. And let me start with a short story, maybe short fact. During my PhD, I was well, I have opportunity to cooperate with many scientific groups, the groups like in Chicago, Paris, Brussels, all over the Europe, also in Poland. Today I calculated that I encircled world twice during my PhD because of the amount of work which I had to do during my studies. And this was like the reason why I had to do this was my motivation to give you this talk titled Beyond Translation, Nature-Driven Deep Learning Architectures for Biological Analysis. So at the end, I hope that this initial story will be clear. So let me start with a short agenda. So I will today concentrate not on all biological problems, AI problems, but on a problem of biological discovery. First, I will tell you why the problem of biological discovery in AI is super difficult. I will later explain you how people usually tackle them, and later I will tell you how we tackle them. And by we mean our group at the University of Warsaw, which is called Computational Medicine Seminar, supervised by Professor Ewa Szczurek. So let's jump in. So, well, I mentioned that I will talk about the problem of biological discovery. So let's try to place this problem in the AI landscape. So if you think about AI problems, I would like to divide them into roughly two categories. So the first category, which I call the average problem, is the problem where you have existing knowledge, either in form of, let's say, knowledge base or data sets, and you want to build a model that on average follows this knowledge, right? So you have loads of headlines that AI is great at this. AI is great at diagnosis, and it's getting better every day. So this is not so hard problem. Obviously, it's sometimes hard, but not so hard. The much harder problem is the problem which I would refer to as maximum problem. The maximum problem is the family of problems where you like to go beyond the existing knowledge. So one of the landmark problem in this set is obviously drug development. We have some drugs. These drugs are not satisfactory. We want to get better drugs. So we want to get the drug that is better than maximum on the set of our existing drugs. And to the same category, I would add the knowledge discovery. We have a knowledge, and we'd like to expand beyond this. And well, obviously this is a super hard problem, because if you think about it, today we have like ICML conference, almost all of the problems on which you benchmark are in this category. Whereas the problems which are super important, obviously they are here, but a lot of them are there. And obviously, because we want to expand, we don't have benchmarks. So this is one reason why these problems are super difficult. But there are other problems that are specific to biology. And one thing that is super specific to biology, especially molecular biology, that this is like highly physical domain. Basically, to measure anything about cell, drug, or protein, there is like a lot of physics and chemistry involved. And obviously, once you have this, there is like a lot of error, like physical error. So let me give you one example of this problem, which is like highly, unfortunately, highly like affects the domain. It's called batch effect. So imagine that you have a patient, two patients, and you have you collect the material from them, and you run your physical experiment to collect some data about it. Well, the machine might have different settings. The reagents might be in different densities. So these things might go terribly wrong, right? So you can have these two patients to be totally separated in this input space. So this is called batch effect, and it's purely because of physics. So there is something which is called batch effect correction, which kind of assumes that, okay, these two things should have the same distribution, so we try to match this distribution. But if you think about it from the biological discovery point of view, this is exactly killing every discovery, because we are assuming that these things are the same. So if there is like a knowledge in one patient, well, this process is actually deleting this information. So the physics is hard here. The other problem here is signal sparsity, and it's not data sparsity. Actually, there is huge problem with amounts of data that are generated. So like usual experiment, and this is like approximation, usually, like for example, if you think about cellular stuff, a single experiment gives you 2 million cells, and the dimensionality of a single cell representation might differ from 6 to few 100,000 even. So there is like loads of data. But usually you collect this data from roughly 150 patients. And this is where the signal is. And it's super hard to kind of backtrack information from there to these millions of data points. So this is the second problem. Okay, so this is like kind of the reason why these problems are difficult. So now let me briefly guide you like how people solve these problems. And because of what I've mentioned to you, like enormous signal scarcity and like a lot of bias, like there are two different ways of how people approach this. When you care, usually the rule of thumb is that if you care about the noise, you simply resolve to simple methods. And I mean really simple. You think linear models, you think basic statistical analysis, basic clustering. On the other part of the spectrum is something which I'll call deep learning. And well, I will concentrate on this over the next few slides. But well, some people think, okay, the dimensionality of data is so high, let's try to throw deep learning on this. And in biological domain, there is a certain way on how people actually throw deep learning at this data. And let me explain this way on a simple example. And well, this is also when translation the main title comes from. So this is like a standard input to your transformer language model, right? So let's assume that you have a word or a phrase that consists of 3 tokens, like token A, token B, and token C. And you obviously have additional information about the position, right? Because transformers are permutation invariant, so you need to include this information. And well, experts in the domain notice that, well, it kind of looks like this, that if I had a cell and I had information about gene expression of this cell, I can look at this vector in the following way, that instead of tokens, I have expressions, and instead of positions, I have genes, right? So this is kind of similar. And let me guide you through three landmark papers. So the first paper is SC-BERT. So once you have this, well, you can train BERT-like mask language model. So this is the first seminal paper. The second paper, GPT, right? People found out how you can train this model or use this model autoregressively. Okay, so I have a quiz for you. So which method does Geneformer use? Which is like, I think the Geneformer published in main Nature. Does anyone know? Okay, so funny thing is that Geneformer actually managed to transform this original problem back to the text problem. So basically they found out how can you sort the genes so you basically don't change anything from the basic LLM models. But here you may see that this is kind of translation. And it's not translation in terms of, let's say, domain. It's not biological. It's purely data-driven. We have a data. We're able to translate our data to the data that is known to the LLMs. And, well, we can go. So, well, in this spectrum, so as you may see here, there is a huge hole in the middle, right? You have really simple methods, and you have like translations of popular deep learning models to biological data. The translation is done on the data level. So here is where we get to how do we, so the group in which I work in, solve this problem, and we call this SLS methods. And this SLS it's not this rocket from NASA. It stands from slightly less simple methods. And well, what do I mean by slightly less methods? These are not super simple methods. So this is one model which we developed in our lab. I am first co-author of the paper. So here we aim a problem of peptide generation, antimicrobial peptide generation. So think about the antimicrobial peptides as short words over 21-letter character. And well, so this is the schema of the model. Well, it doesn't seem simple, right? So let me explain you why is it simple. So this is variational autoencoder, and this is the first thing, like autoencoders tend to compress data. They produce noisy images. So this is like the first sort of regularization that we used variational autoencoder. The second thing, the variational autoencoder part covers like 20% of this image. The rest is biological or optimization regularization, biologically driven or optimization driven regularization. And finally, the model which we used is super simple. It's small RNN, small recurrent neural network. And it's not a transformer. And we tried transformer, but it failed. And let me give you a brief intuition why transformer might fail on this data. If you think about a peptide, like you can see the sequence here, right? You may think that this is kind of similar to language, but our language, obviously in our language, the order is important, but it's not extremely important. You have many ways how you can change order of words and still keep the, let's say, the meaning of the sequence intact. In case of peptides, it's totally different. You will switch one peptide here, and you can go from extremely promising peptide to something what is not even possible to synthesize. So this is a super hard problem. And if you think about from the RNN perspective, RNN's model kind of this sequentiality directly, and there is like a huge line of evidence that at least initially RNNs were better for this task, not transformers. And well, we were good at this. If you look at this left-hand side of the slide, the red. So this is a metric. And think about the area under this curve is your metric. So we are the red model, so the area there is huge. The other generative model class, well, it's low. But there is like one more model here. It's called Joker. And I told you that, well, simple methods are popular in biology. So as I mentioned, this problem is about generating short sequence of amino acids, if someone knows. And this is this Joker model. It's super simple. So how it works? The authors found this short subsequence, and later they took a template and simply throw this subsequence everywhere they could. And this is one of the state-of-the-art models at the moment. So this is the magic nature of biology, that sometimes simple method, if you know the biology behind it, sometimes simple methods are good. Obviously, this model, it can't generate too many candidates. Our model can generate much more, but still, it's a really good model. Okay, and now let me jump into a slightly different problem. The problem on which I worked for, I have worked for the last 2 years. So this problem is cellular data analysis, image data analysis. Well, so this data looks, well, like this, as you may see. It looks like image. So, well, maybe let's throw some image model on this. But it's not so simple. So first of all, this is a tissue data. So if you rotate it, if you apply any symmetry to this data, you will get the same tissue. So this is the first difference. But in general, the main difference is that even that you see some sort of objects here, like some sort of architecture, like everything on, let's say, on the high level and the super low level, it's kind of arbitrary. The fact that you have these, let's say, organs here is kind of arbitrary. It might have totally different shape. And these small details, let's say with respect to cells, they're also arbitrary. They might change. The key information is somehow in the middle. And this is why we introduced the model, which is called childhood, which kind of tries to model this cell information at this, just in between these two levels I told you. So how childhood works? So childhood works in this way that you take the tissue, you extract few neighboring cells out of these. Later, for each of these cells, you collect their information about their marker expression, so what proteins do they have. And later, they are fed from the encoder, so it's transformer. I will explain later why we use transformer there. And for each of these cells, you first generate the cell level representation, which is enriched about the information about other cells. And later, we simply average these cells out and feed it to the decoder, transformer once again, that tries to retrieve back the original marker information. So it's kind of autoencoder. But here's a tricky part. Because as I mentioned, like there are a lot of things arbitrary in this problem. We don't want to care about positions here. We only care about what cells are here. So we treat this table here as a set. We don't care about the order. And these representations there also don't care about the order. So this is why we use transformers. Vanilla transformers are permutation equivariant. So basically, no matter in which permutation you will fit this data, you will always get the same at the output of the autoencoder. So it's super hard to train. So this is why we introduced the permutation model that kind of tries to guess how the input and output to the model differs, and by this enable training. So, well, why this is model only slightly less simple? Let me tell you about the simple models. Well, there are two families of simple models. First family is to take this table and kind of summarize it across the rows, across the cells. You can take average, maximum, minimum of different markers. So, but these methods kind of lose all of the information about which cells are actually there and what their expression, marker expressions are. The other is that take like half of these markers there. Based on these markers, you can kind of guess the type of the cell and only discard all of this information and use only the information about what type of cell types are there. Obviously, this information also loses a lot of information. So we wanted to build a model that is kind of preserves the all information about the cells. And well, we came up that this is the simplest model that actually is able to do this and keeps the information about all of the markers and all of the cells inside. If you come up with something simpler, reach out to me. I would be super curious. And what's super important, because we want to deploy this data on, we deploy this model on this image data, and we want to do some discovery. So we see there are biologists involved. And biologists are, well, people who usually don't trust deep learning methods. So this, I haven't mentioned that, but biologists really usually don't trust deep learning methods. They're usually disappointed with them. So we kind of need to show them that this model works. And how do we show them this? Well, we take the childhood representations of these cellular neighborhoods, and we need to show them that they kind of capture the popular things, the known things about the data. So, but we have found out that if you use this representation, this representation captures so much that we're kind of missing this big picture. So we applied a simple trick that we took these representations, and for the whole cellular neighborhoods in the data set, we applied PCA to it, and we simply analyzed, let's say, reduced representations that came from this PCA. And it turned out that this model captured these generally known trends really well. And this is one example. So this is one of the popular, let's say, MNIST data sets for this kind of data. And so this is a part of a brain. Each spot here represents kind of a cell. And these cells are assigned to different 6 layers of brain. So you have 7 layers. So we have 6 layers of brain and white matter. And as you may see, when we took the childhood representations for this data and we took only 2 first dimensions, we kind of capture everything nicely. And well, I'm glad to inform you that childhood is currently state of the art of the model on this data. And how much more time? Okay, cool. So I put this slide as optional because, well, when I try to give this presentation at home, I have a huge variance in my estimates of the time. So later we actually, so this was a publicly known data set, but as a part of my cooperation, this is why I also travel a lot. I'm in a huge European consortium, which is called IMUCAN, which collected a lot of information about the patient data, cancer data. So here you may see the same example as I showed you before. So this highly simplified representation of childhood that was deployed on the cancer data set. And it turned out that if you, well, here, if you had a look at even first the PCA dimension, so a single number that came from the model, it kind of captured, let's say, the most important, one of the most important statistics in the cancer, which is called infiltration. Let me guide you from that. So in the first column here, you have cell types. So these are cells and there are the cell types. So obviously the red one is tumor. And just to explain you briefly, everything up to orange, starting from red, is bad. And everything green, yellow or green is good, right? So these are cancer cells, which are growing without control. And these other cells are cells of our immune system that tries to kill the cancer. And there are 3 popular, and one more important thing is that there is something which is called mural. Mural is that, okay, mural are other cells which are usually there. So there is some sort of structure right? Because we have tissues, right? Tissues have functions, so they need to have structure. So mural are cells that kind of impose this structure by shape. And our model kind of captures, so as you may see here in the second row, childhood kind of follows from this red, when you have tumor, to blue, where you have lymphatic, where you have immune cells, and in between is this mural. And this is confirmed by these other markers, which maybe I will not explain in too much detail, but basically a single number from childhood explains the most basic story about the cancer. You can either have in the first row, like it's called cold tumor, where you don't have infiltration. You can have highly inflamed tumor, which is on the bottom row, where you have a lot of lymphocytes and immune cells. And in the middle, it's something that you have tumor, you have a lot of immune cells, but in between you have these mural cells, which kind of prevent these cells to get to the tumor. And this is one of the most basic stories about cancer. Obviously, the worst one is on the top. The best one is on the bottom. This one in the middle is somehow in the middle. So when we showed this to the biologist, we gained trust. And now we can, we took more complex results from childhood, we presented to them, and these are now, we are in discussion with biologists to confirm that this might be a valid biological discovery. But obviously this is a tedious process, and this is why this is also super hard to do biological discovery in AI. Okay, so it's the end of my presentation, and let me conclude with this that, well, I told you at the beginning that I travel a lot. And I may tell you that the reason why I travel a lot is that basically you have this group which runs simple methods. You have this, well, they kind of want to run something more complex. And you have this group which runs deep learning method, but usually it's a translation of popular methods from current state of the art. So they're usually not trusted by biologists. So if you are somehow in the middle, right, people really want to work with you. And unfortunately, well, this is a huge problem because there are not too many people who are there. And let me conclude with well, this is like a bittersweet story. One of our cooperators in Canada, well, runs a group at the hospital with extremely expensive stuff to run experiments, to run experimental therapies, and they published paper in Nature, which we wanted to get data from them. So I emailed them, and well, I didn't get a response for 2 months. Later, I finally got the response, and it turned out that 2 of their computational people unfortunately were involved in the car crash. So they didn't have anyone computational at their lab, and they couldn't hire anyone. So for whatever reason, there is like a huge hole there. And if you're thinking about your career or some inspiration and you're looking for something new, I may tell you that this is a really good place to be, and you are definitely needed there. Okay, so that's all from me. Thank you.
Good. Okay, thank you. Thanks, Marcin. Do we have questions to our first speaker? So I will ask first. So, Marcin, what are the plans of you and your research team regarding this project? How would you like to continue?
Well, regarding the models, so obviously we are working, so currently we are working also on other models, and well, now my main plans are to finish my PhD, but after that, one of the ideas which we plan to is to kind of make these models more accessible to people who don't have access to, let's say, computational team or group, right? And so we even thought about some products that will help, or tools that will help them to analyze their data and use this, for example, this model. But obviously, if other models are better, we will obviously use the other models, so that will streamline this analysis for, well, for people with situations similar to which I mentioned.
Okay, and do you anticipate that the newest advancements in AI, like especially large language models, can somehow help you in this?
Well, even now so I can see a few people who are working on similar solutions that use large language models. So what's super cool about large language models that they kind of you can quickly check if the information which you have is someone out there, right? Because LLMs are great also decompressing existing knowledge. So if you run your analysis and you can see some insights in your data, some trends in your data, you can simply ask LLM if this is something known. You can use RAG technique to retrieve the interesting articles. So yeah, obviously this is I think this will be super useful. On the other hand, on this translational hand, I think it's super interesting philosophical question. If this model simply adapted from text to the biological data will excel at in the end, or if there is a need to actually develop methods who are more biologically informed.
Good, thanks. Do we have more questions to Marcin? If not, let's thank once again our first speaker. Thank you, Marcin. And it's time for our second speaker, Kateryna Nikitenko from DataArt.
Hello, everyone. So today when I was coming here, I was told that I need to be accurate, to be engaged and brief, just like TED Talks. I wish. But I promise I'll be as brief as possible, no matter how much time it takes. So AI is only as smart as the data and design that shape it. What if the missing piece to true personalization isn't just the algorithm, but how well we understand the user behind it? I mean, obviously, AI models are very capable while processing vast amount of data. But when you can teach it to recognize a cat, but when someone wants a cat meme at 2 a.m., only we can help you understand why. So today I would like to speak about how UX-driven research and design can help train AI models. And as a proof, I'll use one of my latest projects, training AI model for an investment app. So who am I? I'm glad you asked. I'm Kasia, a UX consultant from DataArt in Krakow. I specialize in tackling complex problems with the research-driven approach, and for some reason I'm all about human-centered design especially for those complex technical products, because no one likes a tech product which feels like it needs its own user manual. So why AI needs UX? As I said, AI models are undeniably capable of processing vast amount of data at lightning speed, but yet their brilliance comes with a blind spot. They are lacking innate understanding of human behavior and decision-making process. So we, as UX designers and researchers, we are injecting the empathy and human-centered approach directly in the AI training pipeline. And institutions like Stanford Human-Centered AI Institute, and yes, that's a real thing for some reason, they tell us that models that trained with user-centric feedback and approach outperform traditional AI models in personalization and engagement. And while actual research studies quantifying the numbers are still emerging, it just underlines one truth, that UX is not just a supporting act in AI development. So, you may still be asking, why am I even talking today in front of you? You're all very technical. I am not so much. But the UX role in AI development is still emerging. The boundaries are not set in stone yet. We are still developing some frameworks, working together. So if you think about the team where some polar opposites like the UX designer and data engineer are working, can they actually work well together? So spoiler, not only can it work, but it also can strive. And there is some even scientific backup to support this thought, obviously done by Stanford, this time with the University of Michigan. They are introducing some kind of desirable leaky abstractions, an abstract name as well. But they prepared some documentation to help all team members, but especially UX designers, researchers, and data engineers communicate with each other in a way that they can understand each other without needing a PhD in each other field. because creating human-centered AI doesn't require the innovation from AI itself. It's already innovative. It requires innovation of how we work together. So when I was writing this speech, when I just started, the project I'm going to use as an example was in a perfect shape, having enormous future perspectives. Everyone is saying that AI is going to save them cost and time, but probably they forget to mention it after it goes live. And as everything in the world has its end, so did our budget. Unfortunately, before we got a working API, despite the fact that we had brilliant results. What we've used for our research, GPT-4o model. We started with 3.5, but we moved to 4o when it went live. And we also used, I would say, our version of reinforced learning from human feedback, because it's not like classical one, but the approach is the same. So the main goal was to understand the decision-making patterns and address them in a meaningful way. So the whole process was intentionally led by UX designers and researchers and product management to focus not on the technology itself, but more on the human-centered approach, on the people themselves, of how they think, what they do, what they need, and what they like. My next slide is just to give you a bit more of a context before I jump into the project I've been working on. So it's like the science behind UX in AI, which is called behavioral science. But since today's case study is about the financial app, it's all about the behavioral finance. And one important theory worth mentioning is prospect theory. It dates back to 1979. Yes, before I was born, but I promise it's still relevant. This theory provides a framework to understand how people tend to feel losses more intense than the gains. And this phenomenon is called loss aversion. It's extremely applicable to investment apps and helps us, UX designers and researchers, to successfully segment users to the respective personas. And but behavioral finance expands on it by understand the high psychological factors like hands behavior, like overconfidence, also impact their investment decisions. So what does the UX designer do to actually support the whole process? We do the research, the ground research, and other types of researches, the qualitative research with the interviews and in-depth studies, some surveys, qualitative studies to triangulate the results. Then we also do the synthesis, and also we analyze the historical data, and obviously throw in some very impressive methodologies with impressive names to just make it look like we know what we are doing. But yeah, for this exact case study and for today, let's keep it simple with 4 personas. So we'll segment them by 2 key traits: low or high impulsivity and low or high financial knowledge and experience. So you will see the persona 1 is low experience, high impulsivity, very enthusiastic, not a great trait in this case, and driven by the excitement, but still lacks the experience and understanding of what they're doing. The persona 2, high experience, high impulsivity, confident, and in this exact case we would need to overcome the overconfidence because it's it just makes them make these bad decisions. Persona number 3, low experience, low impulsivity, just like me, lacks financial knowledge. And persona 4, high experience, low impulsivity, experience, patience, and strategic. I'm still not sure if it actually exists because we didn't meet them. So obviously, in real life, we had more nuances, more traits, and more personas we've been segmenting users by. But this simple framework helps us understand how we actually started. Because at the beginning, we didn't know too many details. We just used behavioral finance, historical studies for segmentation. And to keep things even more vivid, let's focus on 2 polar opposites. The persona 3 with low experience and low impulsivity, and persona 2 with high experience and high impulsivity. And a spoiler, their flows are as different as their personas. So obviously, before we jump into the visuals, the content, the interactions, we need to understand the basics, the flow. But before we even get to that, I mean, the AI model needs to understand who it's dealing with. So magic with segmentation, actually, in this case. So we've been using, for the beginning, with the ground research, which lasted half a year, in the whole the year that lasted our project, quite long, and obviously we didn't expect that, remember, budget. Before we actually could segment these users, we need to had to understand if the questionnaire we've been using actually works, and actually it didn't. So it took us, understand really long to understand why, what happened, and so on and so forth. So even despite we used really, I mean, great historical data, it didn't work quite well. So why these personas are that much different? Because they have different mental models, different ways of decision making, of perception information. When we started the whole ground research, we didn't actually know who we were dealing with, so the personas, everything was changing all the time before we got to some meaningful result after half a year. Can you imagine? Of many, many hours per week we've been doing that, actually. So which is important to know is when we started with the surveys, we didn't work at all. We had to switch completely into the qualitative studies to actually talk one-on-one with people and understand not who they are, but why they are who they are, actually. So these two journeys is the same acquisition flow journey from start to end, but for different personas. And you see this is absolutely different. It doesn't look like, look the same, so we need to empower the AI model not to generate, obviously, but at least to select the right experience. And as you know, in every sweet pot there's a bitter ingredient, and in this case it's bias. So I'm not sure, I think you all know what bias is. But what's important to know here, I mean, it's one of the trickiest challenges in training AI models. And how can it actually sneak in? So it can sneak in through the research planning data. Like, have you ever heard of leading questions? Because we can inject the bias just even before the research even started. Again, you understand why it took us that long. Other thing is like poor demographic diversity, because if you don't do it right, you're effectively teaching your AI model to just ignore some user groups. Addressing bias is not a technical responsibility, it is a design responsibility in the first place, because all of this, obviously, and processing, oh, I forgot about processing, because me as a UX designer, and I've done that a few times, can inject bias directly while the synthesis of the data, which obviously leads us to the skewed AI predictions and recommendations. But good news, I think we can at least try to address the bias. And when something doesn't work, even if you think it does, it's worth using these amazing and very important techniques to tackle bias head-on. Starting from the very beginning, from the pre-processing data. Resampling grouping data, clear, yes. Combining research techniques, again, triangulation. If one research method doesn't catch something, another might. And validating historical data, because let's not pretend some ancient wisdom is not bias-free. It needs a second look. And obviously, in processing, regular audits of training data sets, synthesis cross-check, because two heads is always better than one while synthesizing research outcomes. Obviously, fairness constraints, of course, and avoid an overgeneralization of findings, because no, not every impulsive person behaves the same way. Tackling bias, even when it already happened, yes, it's also possible, better not to get it to that point, but yes, with real-time feedback loops and feedback from real people, we can again train, retrain AI model to get rid of, at least try to get rid of the bias. So sounds fairly easy, right? So no, it's not, but some UX methodologies and UX science always also helps us in this case. We've been talking about the framework to understand the loss aversion and stuff like that, but also cognitive load theory, because it's not just important to feed the user with the right information, but also important to put the vast amount of information in the small pieces, like bite-sized chunks, to our users to be able to perceive that. It's important to ensure that everything works well, because especially in case of my project, finance is a very sensitive topic. So here is, again, sorry, I don't have a PhD, so I have to use my notes. When the ground research is fairly done, it's time for real work, finally. This is a teaser of the research effort. It's a very small part of what we've done for our project. And here on the left, you see this was an initial research plan. So it was cleverly divided by us into two phases. Phase one was all about written content. In the first subphase, we used human written content based on our best assumptions of what might work. In the second subphase, we let the AI reign in this phase, and we used AI-generated content to test. All of this, obviously, with the good old-fashioned iterations. And phase two was we increased the complexity and expanded to not just create the messaging, but also to combine it with the visuals which were created by our design team. So think pictures, icons, colors, layouts, all of this. So the goal was not to just for it all to look nice, but also to work well. And what's that on the right? This is a small snippet of the raw data we've used for that research. Not a big deal. Another one is a quick peek into the process, how the data set takes shape. We start with giving our model some basic information, not too much, because fairness first, but enough to set the stage, a tone of voice, the language, who is the persona, even back to those details like what words should be used, what shouldn't, what phrases should be used, what shouldn't, in colors, and then to get some meaningful result and be able to test it. Take the impulsive persona in this case. So we've created, not we, but obviously I created a really nice example. But appeared that no one likes being told that they're impulsive. Who knew, right? So there was a message that our model created. You're an investor who values security, but sometimes find yourself acting on impulse, especially when the market shifts quickly. While you may feel uncertain and occasionally anxious in high-stakes moments, your curiosity and willingness to explore new opportunities drive you to make decisions on the go. Not bad, right? It's this message sounds okay, but here what real human had to say about it. I don't act on impulse in high-stakes situations. That's not me at all. Absolutely not. I don't make quick decisive moves. But you just confirmed you're impulsive in our questionnaire. What happened? We didn't know that. I still don't, obviously. But yeah. In the end, we went back to the drawing board, refined the message, removed the sneaky words, made the tone more empowering, more friendly, and in the end, we got much better response for the next messages that were created. Now let's talk visuals. I just remind you, these visuals were created by human beings, my fellow UI designers. So this screen is just the same step in the acquisition flow, but for different personas. This one on the left is for generic users. It's fine, functional, and utterly uninspiring. However, these two next are much better. Normally with the reinforced learning from human feedback, we would just ask the user, do you like this, yes or no? But with the research, we've evolved. Now we understand why they like something or don't like. So for Persona 3, the screen looks like this. It's a touch of green, friendly, unintimidating, some smileys to keep things, easy for the start. And for Persona 2, who is, if you remember, impulsive and experienced, direct numbers, minimalistic design, but again, few messages to slightly help them work out their impulsivity without not saying that they're impulsive, obviously. So you see that these screens are words apart from each other, which is very important because it actually helps understand that something is working. Because it's not important. Again, we're not trying to make it look good. We're trying to make it sound right. But I mean, in our research, we've pushed the boundaries even further with experiments, because we've been asking ourselves, how would we do that? How would we show it? What should we do? What should we show? So long, and we were so exhausted out of it, so that we just asked for some help. So this time, it led us to fascinating experiments when the AI model, which we already trained a bit, started ideating with us, and potentially just started noticing the ideas that we just have missed. So it led us to some nice concept like AR and bespoke audio experiences. Like, think, Google is actually doing something like this. So we've been taking some, inspiration out of that. But you just imagine that your investment app is creating a nice podcast for you with specifically aligned text for you and the information you need, where you can ask your question just on the go. So the level of personalization we discussed today is not bespoke in sense of being crafted to a specific individual. It's persona-based. But here's the thing. Personalization doesn't have to be bespoke. It doesn't have to be crafted like in every detail. The magic is to deliver the right thing at the right time. So while now it may sound futuristic, I'm pretty sure this is exactly how the AI and UX development is set to evolve. So if you remember at the very beginning, I've asked you if the missing piece in true personalization isn't just an algorithm, but how well we understand the user behind it. I mean, we need to think about whether there is any future in UX, in AI development. I mean, I personally am consider that there is a future. Just think about real-time adaptive UX powered by AI superpowers, where your app immediately crafts the layout and messaging when it feels you have a decision fatigue or something like that. And predictive UX models take it even further with evolving with user behaviors and predicting what the user would need even before it was voiced. I think it looks great, right? So, I mean, as UX professionals here, we need to come in, because technical solution is not everything, and we as the UX designers and researchers can connect the whole technology with real user needs and emotions. So, I see blue future. I hope you also do. But yeah, when I was thinking how I can wrap up this speech, I was obviously asking my trusted ChatGPT instance for a joke. It still can't joke. And frankly, if AI develops a proper sense of humor, I think humanity might have bigger problems. But since we're on the topic, let me address a common concern. Many people think that AI can take over their jobs. Don't stress too much. I'm pretty sure AI still cannot make a decent cup of coffee, so at least I'll always have a backup career plan.
All right, it's time for questions to our second speaker. I can start because one of the last slides about this adaptive real-time UX was very interesting, and actually I'm curious, what's the state of the art of this? I mean, is AI already applied to personalize user experience and user interfaces, or how good it is already in this task?
As far as I know, I don't know too much, but as far as I know, it is, and it is evolving. So, I mean, if we talk about the personalization per persona, yes, it's very much possible now, right? Especially since this wouldn't be a real app, that would be just an API, which is not like the first idea in the market. But yeah, but if we talk about like predictive AI and predictive UX and crafting the interface on a go, I just think it's very near future rather than something already existing.
Okay, good. Do we have more questions? Yeah, there's one.
Hi, thanks, great presentation. Quick question, something that resonates with me recently is that due to the rise of agents and operators, actually the GUI will become API. And how do you think the idea of persona fits to that, where the operator will be representing the physical user, and will the operator / agent have the persona where the UX will have to adapt to, or the communication between the agent / operator will be limited just to the data exchange, because in the end, artificial intelligence doesn't need the graphical interface to communicate. And did that resonate with your team during your work?
I mean, the only reason why we had the graphical interface was to test, because, you know, people, like human beings, they are not tend to understand just the data itself without any visual representation. So the only reason why we actually did this was to help us with our testing, nothing else. But if we talk about the personas, in this case, I personally think that, you know, it's like an old sentence, but I think it's still applicable, that a product for everyone is a product for no one. So I'm pretty sure it should exist. If it would, I don't know.
Okay, does it answer your question? Good, thanks. Another question? Okay.
Hi, at the beginning you said that a project ran out of money, which is typical for projects. But from your experience, how much you were from making something actually useful, marketable, you know, deployable? What would you like to do to really work with that tool in your own work day to day?
I mean, if we talk about marketing, it was already marketed to, I mean, it's obviously not on this market, but on the UK market, it was already marketed and a huge interest was raised. The only thing why I'm not working on the project now, because they lack the budget for research, which I'm actually doing. But generally, I'm pretty sure they're very close. I mean, a year, even less, to the working API.
Okay, thanks.
Yeah.
Do we have more questions? Oh, I don't see more questions. Okay, thank you.
Yeah, thank you very much. May your algorithm always hit the mark.
All right, so now it's my turn. So my slides are not as nice as in the previous presentation, but I hope you will enjoy and like it. So I will tell you about traffic signal control with reinforcement learning. It is in some sense continuation of my PhD research that I completed last year, and I'm working on it together with several other researchers from the TensorCell research group. So at the beginning, I'll also tell you a bit more about this group. This project is formally supported by the Quantum AI Foundation that I also founded. So TensorCell is an independent research group which is started in 2016 to facilitate research on optimizing complex processes using AI. So we focused on optimizing traffic in cities from the beginning, but this is not the only complex process that we try to tackle. There was from the beginning remote-only collaboration, and so far there have been more than 70 people involved from different universities and companies. We try to publish papers at good conferences, like we have 3 publications at the workshops of the NeurIPS conference or the publication at the MTITS. And at the beginning, we focused on approximating the outcomes of time-consuming traffic simulations using machine learning models. So today, the very popular concept is knowledge distillation. So in some sense, building such meta models or the surrogate models was also knowledge distillation from microscopic traffic simulations, not from other machine learning models, but we trained machine learning models on inputs and outputs from the traffic simulator to just calculate some traffic characteristics faster. And then such models were used to optimize or find optimal traffic signal settings. And finally, we started working on applications of reinforcement learning to traffic signal control. Because when I designed also my PhD thesis, the complete system for traffic signal control, there were some, let's say, offline components in which we can collect traffic data, like information about the speeds, positions of cars, or traffic congestion offline, so not online or not real time. We can, let's say, cluster traffic data to detect some typical traffic profiles, like typical profile of traffic on Thursday afternoon in Warsaw, like today. So every Thursday, people as you travel from more or less the same areas to more or less the same areas, from the work to your homes usually, or to do shopping first. So there are some patterns, there are some repeatable patterns that can be inferred. But of course, there's also noise. There are some fluctuations because traffic is not always exactly the same. There are always some fluctuations. But for these typical profiles, we can already, let's say, train some machine learning models and apply optimization algorithms to find good default traffic signal settings, let's say, that could optimize our travel times, let's say. But then when we have online data, it may turn out that the traffic is totally different than we had in our, let's say, training cases. So we should somehow adapt our default strategies. And there are several ways to do it. But one of the approaches that we investigate is based on reinforcement learning. So I believe that many of you, maybe all of you, or almost all of you have already heard about reinforcement learning. But just to recall, in reinforcement learning, we have an agent, or potentially we might have many agents, learning how to act in a dynamically changing environment. So we have an environment. Very often it is just a simulation in which there are some states, and our agent or agents observe the state, current state, and based on the observation, the agents take some actions and make decisions, and after taking actions, they get some rewards, which are used to just tell the agents whether the actions were good or not. And based on such feedback, the agents just try to improve their strategy and decision-making process in this environment. And as you can see, the problem of controlling traffic signals is quite good use case for reinforcement learning algorithms, because we can think about an environment, simulation environment. So this could be a traffic simulation. And in this traffic simulation, we have different states. So they can be represented as, let's say, vectors of numbers of cars or average speeds at different road segments. We also have some actions. So the actions of traffic signal controllers are just decisions how to modify the settings of traffic signals. And we may have some rewards, which can tell us about the quality of traffic in a given time period, like about the total time of waiting, the total travel distance, or the amount of consumed energy, depending on what exactly we would like to optimize. So actually designing the proper reward is very important in reinforcement learning. So this was a motivation that perhaps reinforcement learning could be a good approach to tackle this complex problem of optimizing traffic signals in cities. And in the first experiments that we ran already a few years ago, we implemented a very simple traffic simulator based on the so-called Nagel-Schreckenberg model, which is a mathematical model, the so-called microscopic model, in which every car, every vehicle, every traveler is represented as a separate agent. So this is an agent-based model, mathematically modeled using cellular automaton. So maybe some of you have heard about the game of life. So this is an example of a cellular automaton. So originally, this model was used to simulate traffic on highways, but it could be also adapted to urban conditions, and there might be also some deterministic variants. The state, representation of a state could be a vector of average speeds and the number of cars per a given road segment. And in the first experiment, each state corresponded to one cycle of traffic lights. And the action could be just an offset, for example. So the offset is the number, time in seconds from the beginning of the simulation to the first switch of a signal phase from the red state to the green state, right? So this is just this could be an integer number, and for all intersections, we just need a single number in this case, assuming that durations of green and red signal phases are constant. And finally, the reward was the total distance covered by all cars in one step of the simulation, so between taking two consecutive actions. We train the DQN algorithm, which is one of the, let's say, most popular and frequently used reinforcement learning algorithms. And there were also relatively simple traffic networks used. In the first case, there was just a single lane road with 4 intersections. In the second case, there was just a grid, 4 times 2. So basically, the idea was to see whether we can, let's say, learn, or whether the agent can learn to do something or create something like a green wave. And this was summarized in bachelor thesis of the students at the University of Warsaw that they supervised a few years ago. And even in the first experiments, it turned out that we are able to produce strategies giving a better average speed, better than the baseline, which was just selecting some actions, so changing traffic signals randomly. So it was not a huge achievement, but it showed that we can already get some meaningful results. And that reinforcement learning could be a good approach to tackle this. So later I was contacted by Professor Kim Lim from Technical University in Malacca in Malaysia. And together with his team, he did something very interesting. So first of all, he's a rather traffic engineer, so he's not a computer scientist. But together with his team, they installed cameras at different intersections in Malacca. So here we can see just a location of one of these intersections on Google Maps. What is also interesting in case of Malaysia is that traffic coordination there is different than the traffic coordination in Europe or in the US, because we are rather used to this kind of coordination when, let's say, if there is a green light from north, then there is also a green light from the south, and there are red lights in the, let's say, the crossing directions. But in Malaysia, when there is a green light from only one side, and there is a left side traffic, and there is a red light from 3 other directions, right? So it's a bit different, but basically the strategy of representing the reinforcement learning agents is similar, because as you will see, the actions can be represented in a similar way. Okay, so this team from Malaysia installed video cameras at this intersection, or maybe even a bit larger area. And the video cameras were also equipped with computer vision algorithms responsible for not only classifying vehicles, because this is relatively easy task, but they also recognize the car plates. It's also not that difficult already. It's doable. But thanks to that, they were able to monitor every car in the given considerate area in the city. So thanks to that, they had very good information about the exact travel times in every direction. And also about the so-called origin-destination matrix. So in traffic engineering, the origin-destination matrix is a square matrix in which every row and column correspond to a given area, and a cell in the matrix just indicates how many cars or how many travels do we have from one origin area to one destination area. So that's why we have the square matrix, and by just monitoring the traffic using computer vision methods and video cameras, they were able to build such a matrix with very good accuracy. And thanks to monitoring the cars and recognizing the car plates, they were also able to calibrate a traffic simulator to replicate real traffic conditions with very good accuracy. Here you can see a histogram of vehicle journey times between 2 areas in the considered area, right? So these are information about the travel times and the percentage of vehicles with the considered journey times, and you can see the data coming from real-world measurements and the outputs from the so-called Sumo simulator. So Sumo is one of the popular traffic simulation tools. So you can see that there was quite good conformity between the real-world data and simulated data. So they scientifically prove that in some sense the simulator is able to reproduce real-world traffic with quite good accuracy. So this was a very good environment for us to test some reinforcement learning algorithms, and we also had quite good baseline benchmark algorithm. That was the basic coordination plan derived based on the so-called Webster algorithm. So the Webster algorithm is an algorithm developed in the 50s of the 20th century, so many years ago, but it's still frequently used for traffic engineering purposes. So here you can see the 4 different phases corresponding to these 4 different directions from which we have green lights. And here you can see durations of each phase for each of the 3 intersections. Yeah, so this was our benchmark. So in the next experiments, we of course use this calibrated simulation tool and OpenAI Gym framework. The states were also represented as vectors. So there were just number of cars at this 11 incoming entries, 11 because there were 3 intersections, 4 entries in 2 cases and 3 entries in 1 case, plus phases at 3 intersections. So just information about the current states of these traffic signal controllers. The actions were binary for a given intersection. So that was just a binary decision whether to change the phase to the next one or not. So that was a binary decision for every intersection. So in total, there were 8 options for 3 intersections. Because there was only, at the beginning, there was only 1 agent aiming to learn how to control these 3 intersections at the same time. And the decisions were taken once per 5, 10, or 15 seconds. It was also assumed that the maximum duration of a signal phase is 90 seconds, which means that this signal phase cannot be extended more. And there were several reward functions corresponding to difference in the, let's say, current waiting times for all cars at the intersections, difference in accumulated waiting times from the beginning of the simulation, difference in average delays of cars, difference in number of cars that pass the intersection. Later, we also implement a few more rewards, and there were also 9 metrics, but 2 of them were the most important, or at least after analysis, we consider them as the most important metrics for us. The number of vehicles that completing the journey during 1 hour of simulation, and the average of all delays of all vehicles that completed the journey. Where by delay, we meant the actual travel time of a given car divided by the ideal, so free flow travel time with the maximum speed. So that was the delay. And of course, we wanted to minimize the delay, but maximize the number of vehicles that completed the journey. There were 3 considered traffic scenarios coming from this real-world traffic detections. So we focused on 1 hour traffic between 7 and 8 a.m. in the morning on 3 days. 2 of them, 26th of November 2020 and 18th of March next year, were Thursdays, and 29th of November was Sunday. This is also important. In some experiments, we used randomly generated scenarios based on data from 26th of November for training, and then trained agents with, and then the agents were tested on the original scenarios. So here the idea was that we want to test our agents on the original scenarios corresponding to real traffic in Malaysia, in Melaka, but we should assume that in the training, we do not have access to this real data, real traffic data. But we know that there are some patterns in road traffic, right? So we can assume that when we collect data from consecutive Thursdays, then there are some patterns, but there are also some fluctuations. So in the training procedure, we introduce these random fluctuations. So we introduce some random changes to the original real-world scenario, and based on this, let's say, randomly modified data, we trained our agents, and they were validated on the original real-world scenario. So initially, there was still 1 agent. It was assumed that there's 1 central traffic signal control responsible for all these 3 intersections. And there were 2 algorithms tested, PPO and DQN. They are both quite popular in reinforcement learning. They were relatively simple neural networks with only fully connected layers. When we have only 3 intersections, then there is not much space to, let's say, play with some sophisticated architectures. And we monitor the results in the Neptune framework. Maybe some of you heard about it or use it in your work. You can collect all the metadata about the experiment. So based on the identifiers, you can see that we really run hundreds or later even thousands of these experiments. And we are easily able to monitor the progress of training, in this case on validation scenarios, so these real-world traffic scenarios, in consecutive iteration, consecutive episodes of the training procedure. So some conclusions after the first experiments. The first conclusion was that it's easier to obtain good results when we train and test our agent on exactly the same traffic scenario. So when we want to overfit our agent to some single traffic conditions that we exactly know precisely, then it's relatively easy, and it's something that we expected. It's also easier to obtain good results when we have fewer cars and only two phases. So in some experiments, we assume that we want to just replicate something like a green wave and assume that there is only a traffic on the, let's say, the main arterias, and there is no traffic coming from some neighboring roads. So there are only two phases in one of the two directions. And it turned out that it's also relatively easy to outperform our baseline at the Webster method. It's difficult to obtain good results when we train models on different traffic scenarios and test on other scenarios, which is a real-world reality, actually. The best results were usually for the reward being the difference between accumulated times of waiting. And for DQN, we got lower values of the examined metrics faster, but it behaved unstable, especially for high traffic, like middle of the week. But in contrast, the PPO algorithm needed more time to discover the best signal setting solution. However, it led to less discrepancy in learning, which had become smoother over time and more stable. And later we learned about very interesting framework developed by researchers from University of Texas. And there was even a paper at the New RIPS conference about this framework. The title is Reinforcement Learning Benchmarks for Traffic Signal Control. And in this framework, there was also exactly the same simulator use, Sumo, so it was easy for us to integrate with the RESCO framework. And there were also two, let's say, another benchmark real-world scenarios from two German cities, Cologne and Ingolstadt. But we decided to focus still on the Malaysia use case. One of the main differences between our original approach and this RESCO framework was that we used independent agents. So it was a multi-agent reinforcement learning in this case. So there were separate agents responsible for different intersections. So that's why the algorithms were called IDQN and IPPO, I from independent. There was one agent per intersection, each with convolution layers for lane aggregation, and later there were only fully connected layers. There was also a new reward, a combination of the number of cars and the total time of waiting. And in general, RESCO allows to easily define some other metrics as well. And after really thousands of experiments, starting from about 2011, we finally managed to outperform the Webster method, even in the most difficult scenarios in which there's really heavy traffic. And it seems that even for human expert, it might be difficult to design a traffic signal control algorithms properly. And we managed to outperform this Webster method in all the metrics that were tested, corresponding to the average delays and the count of vehicles completing the journey during the simulation. Which is a very good result in my opinion, because they were achieved on real-world traffic scenarios, realistic traffic scenarios obtained from measurements of real-world traffic data. Of course, there are many other papers and approaches, so the interest in applications of reinforcement learning methods to traffic signal control is growing, but one of the biggest issues is that it is hard to get good quality real-world traffic data. So I think that we are very lucky that we are contacted by those people from Malaysia, and they managed to build this very accurate traffic simulator with good conformity with real-world traffic data. So one of the current ideas is to train the models on synthetic data generated using computer simulations, and then fine-tune them on data from real-world scenarios. So the synthetic data can contain different topologies of the road network, different traffic conditions for the same topology. So we want to have let's say, something like a fundamental model for traffic signal control that could be later fine-tuned for some specific real-world scenarios. We also consider some other approaches, like, of course, testing more sophisticated architectures based on graph neural networks, on graph attention networks. So in general, taking into account some information about the topology of this road network graph, and also maybe some information about both temporal patterns and spatial patterns. So there are some ideas to combine convolutional layers with some recurrent layers. But there's also a very interesting idea that emerged about 2 years ago to use LLMs, so traffic signal control agents. So just a few years ago, it would be probably hard to believe, but currently this is also one of the state of the arts in the research on this topic. real-time traffic conditions can be just given as an initial prompt for LLMs, and then LLMs can be applied to traffic signal control, and it also gives very good results. And what is also interesting is that currently we have plans to run a pilot project in the Smart City Lab in Chełm. So it's a newly established Smart City laboratory. Currently there are also plans to build a similar lab in Lublin. So the person who is in charge, Dr. Marek Litwin, saw a similar laboratory when he was a PhD student at the University of Toronto, and then he came back to Poland and is trying to establish similar labs in different cities. So we also try to help him with this. And finally, we are looking for collaborators. So if these topics are interesting for you, I also invite you to join us. Of course, this research was not done by one person. There was a huge team behind. There are several current team members working with me, and there are also several former contributors. So I thank you for your attention. I hope you enjoyed this approach, and if you have any questions, I'll be happy to answer. But for the questions and Q&A, I will ask Piotr to help.
Okay. First of all, congrats for your great PhD work. Okay, any questions?
Because the data that you mentioned, the real-time data, and it's costly, and it's like hard to get, and hard to build the infrastructure to obtain such data and collect it. Do you believe that such approaches and such models can be applied more locally? Because you mentioned like grids of intersections and so on, but for example, do you believe that it can be used for like only one intersection, and with enough information about the whole structure of the intersection and the traffic? Do you believe that it can be applied for one specific intersection?
Yes, and there are also such research works. There are many papers on this, not only using reinforcement learning, but also other algorithms. So controlling a single intersection is relatively easy, I would say. So even actually there was Webster algorithm was also originally for just a single intersection, but of course we can apply it to all the intersections that we have in our network. But when you have the reinforcement learning, there is an opportunity to learn how to coordinate these controllers in larger areas, I believe. And that's why we also mentioned this, let's say, graph-based architectures of neural networks that could really take advantage of the information about the graph, which are relatively sparse. So these architectures may even have much fewer parameters than fully connected neural networks. They may seem to be more advanced, but actually, when we look at the topology of real-world road networks, they are relatively sparse, and there are not that many connections between nodes. Mm-hmm.
Yeah, so a question. I might have missed it, but do those traffic lights, can they react to the environment, and then those signals affect your algorithm, or your algorithm is more of a writing a code, more like some program that runs the whole network of those lights, and then it acts no matter what happens, it always acts the same, or does it react to the changing environment?
It reacts to the changing environment, yes, because that's why we train these reinforcement learning agents. Mm-hmm. They take into account the observations of the states, right? So we assume that these data are taken or are given as an input to our agents. So of course, first during the simulation, the agents have to learn how to act for different incoming traffic data. But later, when they are trained, it's also assumed that they should take these different states, and then depending on the states, the actions could be different.
Okay, but so the question is, what kind of inputs because if we are designing the system, yeah, what kind of inputs the single traffic light can take in, so mm-hmm. it will affect your algorithm? Is it like camera image, or do you have some other sensors?
We assume that it's already, so it can be data from the cameras, but we rather assume that so in this case, number of cars, right? So they can be taken from the images, but there could be also some other sources of data, like almost everyone travels with some mobile devices, right? And based on the data, we can also infer the information about number of cars. There might be also some radars or inductive loops. This is a very frequent method to calculate the traffic congestion, right? So there might be other techniques.
So sorry for being a pain in the ass and like hogging
no
the discussion, but are there any right now currently, is any manufacturer of those traffic lights doing anything that is remotely smart? Or not really?
So of course there are adaptive traffic controllers. Yes, there are some algorithms, but I'm not aware of any, let's say, professional system, at least installed here in Europe, that takes advantage of reinforcement learning. So as I've told you, there are many research papers on this. So it's a really growing research area. So it's not difficult to guess that most of these papers are from China. I'm not sure what's the current state of the art of this LLM's approach, but before that, most of these interesting papers on RL methods for traffic signal control were from China or researchers, or from the US, of course, as well. Yeah, so from the scientific side, there is a huge interest on this, but it's not that easy to implement it because it's expensive to get real world data, you know. So it's not that easy, and I think this is one of the issues. But I'm pretty sure that perhaps somewhere in China or in general in some Southeast Asia, such systems are probably already deployed. And one interesting thing is that. You know, I told you that we are very lucky that we are contacted by those people from Malaysia, because they use cameras to recognize the car plates, and based on that they were able to build these very accurate traffic models and to scientifically prove that there is good conformity between simulation data and real world data, right? So they proved that the histogram of travel times were very similar. But I'm even not sure if it is allowed in the European Union to collect and process car plates identifiers in such systems. For sure, it is allowed when the authorities want to give you yes, a fine. Yes, give you a fine. Then it is allowed. But I'm not sure if it's allowed for other purposes. in Malaysia, it was allowed, as far as I know.
All right, another question.
What was the motivation for the independent traffic controllers? Because I imagine that that one that knows everything, this
yes.
would be more powerful than independent.
This is a very good question. So one reason is, so there are two reasons, one experimental reason and one theoretical reason. So the experimental reason was that for a very long time, for several years of running experiments, we were not able to even get close. I think I didn't show these slides, but I have some backup slides to show you, to demonstrate to show you some results of training. So these are the results, like the total average delays, right? So still the Webster method was much better than all the reinforcement learning algorithms that we tested with just a single controller. So this was the experimental motivation, that we were not able to get as close to our benchmark designed by a human expert. And the theoretical reason is that the space of states and actions is very large. You know, the representation of the states is just a number of cars on 11 incoming entries and 3 phases of intersections. There are 8 options for the actions, but the size of the space is quite large. So the training of the reinforcement learning algorithm should really probably take a lot of time to explore such a large space of options, because these are different options, right? These different policies, different strategies, how to act in different states. But when you have a single agent, then the dimension of the space is smaller. The dimension of the space of actions is smaller, so it is easier. But of course, you need to ensure some kind of coordination or cooperation between these agents. And this can be also implemented in several ways. Like they can also share some information. They may share some observations, for example. Yeah, so that was, let's say, the theoretical motivation that by using this multi-agent approach, we can just get rid of this curse of dimensionality in this case, and this approach should be scalable, or it has chances to be scalable. But maybe one last thing, we are also thinking about, I didn't also put it on the slide, but we are also thinking about an approach in which there could be one something like a master agent giving some hints to other agents responsible for each intersection, or maybe a group of intersections. So there could be, we can also think about some kind of hierarchy when there is one master agent at the top and there are some agents responsible for some areas like districts in cities and so on. And at the bottom, there could be agents responsible for each intersection, of course. But again, the question is if it's scalable.
Yes, I have also one question. Did you check how only one agent would work? I mean, because I can imagine that we want to have such agents, such devices everywhere, but we would start from probably one. So how only one would work if you, for example, put it at this cross section here?
So one agent and only one intersection, right?
Yes, exactly. I mean, we can like measure the time, the delay time, and so on, but like we have to start somewhere.
Actually, I think we didn't run such experiments, but based on the results that we achieve, I expect that it should be a relatively easy task for reinforcement learning. But you know, the outcome could be that optimize the traffic at one intersection, but at the cost of making the traffic worse at neighboring intersections, for example, if there is only one such agent. So it may happen.
All right. And the last question?
Sorry for making this longer. Correct me if I'm wrong, but what about temporal information in this model? If I understand correctly, you embedded this information by averaging, but what about using the model that covers this temporal dimension?
We haven't done it yet. I said that we also have some plans to, let's say, test more sophisticated architecture, because from the perspective of machine learning, the neural networks that were used for training are really easy, or so really simple, right? So they are not sophisticated. There was no information about there was no spatial information about the topology of a graph, but actually you are right that even with such a relatively simple case, we can already try to take into account some temporal patterns indeed. I think we haven't done it yet, so this is another area that is worth exploring, definitely. Thanks.
Okay, all right. If you have more questions, feel free to ask in the after party section.
Thank you. All right, so that was the last talk. So thanks once again. And I just want to recall the 3 ideas, or actually one is not very new, because this is the 5th edition of the Quantum Machine Learning Conference that we'll organize in March. But there are these 2 new ideas that we have for the new projects that we would like to launch this year. So we would like to talk about them. This is also a good opportunity to discuss for the after party. Enjoy. So Teresa, I think we can start the after party officially. So thank you once again. Now the fridge is yours. Thank you.